So we are going to have the test on the 25th is actually the Thursday. So we'll review for the test the 23rd. The test will be on the 25th. It will only be on chapter 11. I'm not going to get to chapter 12, which is
on the 25th, you said?
Yeah. So reviews the 23rd, test is the 25th. And then we'll review for the final week after that. And then your final is on May 7th. So. Okay. All right. So we spent all this time doing series, and I've yet to actually show you, like, we figured out, okay, here's a convergence, here's divergence, stuff like that, but we really haven't looked at why we care.
I think I asked you why when we started.
Yeah.
You said you would get to it.
Yeah, it was like, one of those things, like, why do we care?
I mean, I'm anxious.
So a lot of the things, when we look at series, one of the things that two mathematicians figured out, and hold on, I'll get their official names. I know their last names. I don't know their first names. It's Taylor and McLaren, McLaren, but I can't remember their actual first names. Where is? There we go. So Brooke Taylor, he was an English mathematician in the late 1600s, early 1700s, and Colin McLaren, who was a Scottish mathematician. So the Scots and English were working together. Who lived around the same time, just a little later than Taylor did. So they came up with a way to basically take a series and use it to model a polynomial or basically allows them to figure out like fractions and decimals and estimations and those type of things long term. So we learn all the rules for a series so that, because in essence, your computers and everything else that use those things to estimate your answers, to give you those things, is used these type of problems to do it, because it's a series. They just keep adding terms together, which a computer is really, really good at addition, subtraction. Believe it or not much else. Everything they do, they kind of break down into those two basic functions. And it's all basically just addition, because subtraction is just the opposite of addition. So it breaks everything down into that as much as possible to be able to come up with our answers. So they came up with a way to do this. Now, they did this way before computers because people needed a way to be able to estimate answers and be able to estimate what those polynomials go into or what that answer would be and those types of things. So that's why we learn a lot about series. So we're going to look today, we're going to start looking at what's known as power series. So a power series comes in this format. And you'll notice the only major difference between this and what we've talked about before is there's an X. So the power series basically is going to give me a infinitely long polynomial. Okay, it's going to give me x squared, x to the third, x to the fourth, and so on and so forth. Depending on what the x is, depending on what the coefficients and stuff like that turns out, determines if this is going to be a convergent series that we're going to be able to do something with it, or it's going to diverge. What we're going to look at first is how to figure out where it converges, where it diverges, and what's known as the radius of convergence and the interval of convergence for whatever power series we're looking at. Okay. All right. So here is a couple little examples of a power series. So we have this one. What does this look like? What series does this look like that we've talked about? Yeah. I take that back. P is where the exponent or is the variable. This one's a geometric series. This geometric series is a raised to the nth power. So where does a geometric series converge?
Formula, right?
Nope. There's a rule for figuring out geometric series. Not greater than 1. Greater than 1, it diverges. Yeah, that's P is what you're thinking about. So geometric was that ratio has to be between -1 and 1. So as long as that x value is between -1 and 1, that will converge. If the x value was greater than 1 or less than -1, it would diverge. So that would be known as my interval of convergence. We're going to look at it, figuring out exactly how to find those and stuff, but some basic ones we can look at like that. Okay. All right. So let's look at this one. That was basically, we're going to now do something. Yeah. The other one you can look at as a P series, but that 99% of the power series uses a geometric series to do it. So if you look at like this, that's basically this one. All I did is I just ignored the coefficient in front of it. All right. So a power series, so this is an example of a power series. Typically you end up looking at it with parentheses. So with this one, we have that parentheses in there. So this is a slight modification of what we just looked at. This is known as a power series centered at A. Now think back to like your polynomials and stuff when you're doing your transformations. Remember, always inside the parentheses was opposite of the way you wanted to look at it. So that's why it's always a minus. So this one would be moving to the left or compared to the right. So your first term, if you plug in, just gives you your coefficient because it's raised to the 0 power. And the 0 power is 1. And then everyone after that is going to give you your first degree, second degree, third degree, fourth degree, and so on and so forth. Yes.
Why does this one start with n equals 0?
Same thing with the
Oh,
these.
that's what it is.
That's okay. This one starts at n equals 1. Why? Look at the problem.
Oh,
Right. That's why. And that actually, in the end result, that doesn't make much of a difference. You just won't have an initial coefficient in front. You'll start off with the first degree. So, and that's fine. All right. So we've got the series of x minus 3 to the nth power divided by n. We want to know which values of n will make this converge. And that's really the change from the other problems. The other problems is I gave you a problem and we asked, does it converge or diverge? And it would only do one of those things. Because this now has a variable built into it, and that variable can be a variety of things, these series will converge for a certain set of values. Great. and diverge for a certain set of values. And we need to figure out which those values are. Technology is not being my friend right now.
Turn that class outside. Telling you. They even gave up.
All right, so we're going to do this. My life harder to make the file for you afterwards. Which is fine. So last class, we looked at some tests. Which were the tests that always worked and gave me the two things? It says it converged if this happens and diverged if this happens. Yes. The ratio test and the, well, the absolute convergence would do it, but it would get, there was two tests that gave it. One was the ratio test. The other one was what? The root test. Yes. Those are the two tests that would give me those things. Those are the tests you typically want to use with these type of problems, because it's going to give me an equation at the end where then I can then plug it into that rule that I had and go, okay, now solve for X and figure out when it's going to work. All right. So first thing we're going to do is we're going to do the ratio test on this. What does the ratio test say? What was the ratio test?
If the length of the is less than, yeah. I'm sorry.
Of
I have
a
bad allergies.
n plus 1 over a n
Yeah. Equals L is less than 1.
is less than 1, right?
Yeah.
And it was the absolute value of that.
And the series actually.
Correct.
At least that's the first part.
Right. And then if it was greater than 1, it was divergent.
Yep.
And if it equaled 1,
Try again.
we have to try again. So we now have a situation where it's like, okay, I want to know where this is less than 1, because that's where I want to find out that's convergent. So let's look at this problem using the ratio test. So the first thing I need is an plus 1. So that's x minus 3 to the n plus 1 over n plus 1. And then an is x minus 3 over n. And we're dividing those. All right, so x minus 3 to the n plus 1 over x minus 3 to the n. What does that reduce to? X minus 3. Because remember that this is really x minus 3 times x minus 3 to the n. Because I can basically pull out that plus 1. So those are going to cancel out. And now the limit as, so n over n plus 1, that's 1 over 1 plus 1 over n, right? Which goes to what? 1. So this whole limit and everything else ends up coming down to x minus 3, the absolute value of x minus 3. Is less than 1.
Then we just.
So are we good to there? Yes.
I'll do this thing one.
Because the ratio rule. The ratio test says if it's less than 1, it converges. So the ratio test basically says that limit that I just did, if it's less than 1, it converges. And that's what I'm looking for. I want to know where it converges. That's why we're using the ratio test for this and not some of the other tests. Because this one gives me a very specific thing. It says if this is true and it's less than 1, then it works. Because now I can take that part there and solve it for x, the values for x that are going to work for this problem. Yes, your question.
I was gonna ask, so you just solve for 1 and if x is less than
If the absolute value of x minus 3 is less than 1, then we're good. Now we have to solve that problem.
1, how do you know that's true? Maybe I'm not understanding it.
Okay. All right. That's the ratio test, right?
Yeah.
So it says if this is less than 1, it's convergent.
Well, if it's less than
Right. If this is less than 1, it's convergent.
Yeah.
Okay. We just did this.
Sure.
That's what we did here.
Yeah, the limit of
All that
a of n plus 1 over a of n is, you do all that. you
comes
get
out to be the absolute value of x
value
minus
of
3.
x minus 3. Okay.
We're good to there?
Now, how do we know absolute value of x minus 3 is less than 1?
We don't. We're setting that less than 1 because this limit was that.
Oh, so,
I want this.
so we're not done.
We're not done. No, we're not done. I still have to find my x.
All right.
So I now said if this is true, it is convergent. So now which values of x is going to make it convergent? Okay, so now I have to solve that.
Yeah. Less than 4.
So I have the absolute value of x minus 3 is less than 1, which is the same thing as saying negative 1 is less than x minus 3 is less than 1. Now we add 3 to all the sides. So 2 is less than x is less than 4. So if x is between 2 and 4, it's convergent.
And that's our answer. When x is between 2 and 4, it's conversion.
Almost.
So,
Yes.
how did you get to that second step?
The absolute, this one?
Yeah.
So the absolute value means, remember, basically eliminates your sign, right? So a couple different ways you might see this written. You could say x minus 3 is less than 1. And then you could basically take the x minus 3 is greater than negative 1. You multiply both sides by negative because that could be negative. So it's actually this. Negative is less than 1. Those would be both statements. Because if the inside is negative, I'd multiply by a negative to get rid of it. And this becomes x minus 3 is greater than negative 1. Which you just basically put together as one statement.
Can you arrive at the same answer if you
Did it separately?
split it up and then
Yes.
algebraically do it for
Yes, you can you'll get the exact same answer doing it twice. So you do x minus 3 is less than 1, so x is less than 4. Then you have x minus 3 is greater than negative 1, so x is greater than 2 there. Then you just have to go, okay, we have to put these back together. So this would switch around as 2 is less than x, which gives you end up that piece. Because the x's go together. It's just way easier to do it in one step instead of 2. But the answer is going to come out to be the same either way. All right. So if I plugged 2 into this problem right here, what do I get? I get 1, right? What happens with the ratio test is 1 with 1?
You have to try something else.
I have to try something else, right? So if I plug in 2 and I plug in 4, I get 1. Neither one of those is going to work with the ratio test.
Well, that's why we don't have to do less. But you can-
Right. However, this series, we did the ratio test, said, okay, it's less than 1, but the ratio test is inconclusive when it equals 1. So what I don't know is, well, what happens when it is 1? Will it work? Will it give me a series that would converge? Because that is a possibility. Okay. So we now have to test the 2 endpoints. We have to plug in those 2 endpoints. We have to plug in 2 and we have to plug in 4 to see if they will work. If they work, then I have to add the equal to on those sides. Okay. So in this problem, if x equals 2, because that was one of my endpoints, my series is 2 minus 3 to the n over n, which is -1 to the n over n. Is that series convergent or divergent? What type of series is that?
It goes back and forth.
It's alternating. This one has a very specific name. What's the 1 over n? Harmonic. So this is an alternating harmonic, so this one converges. We saw that last class when we looked at the alternating harmonic series. That one converges because that was the series that it was conditionally convergent. It converges when it's -1, but it doesn't converge when it's 1, because it's the regular harmonic series. If we look at x equals 4, we get 4 minus 3 to the n over n, which is 1 over n. Now that is the harmonic series, so this one diverges. So the x values for this one, 2 is less than or equal to x, is less than 4. So that would be my final answer. We get the 2 to 4 with the ratio test, and then we have to test the endpoints because the ratio test doesn't work when it equals 1, which is in essence what we're finding when we do this. You're not finding when it's less than, you actually are finding when it equals. We just have the inequality symbols there to find your range. So, okay.
So so if it converges, then you include it.
Right. Yep. Then that endpoint is included. All right. This one. All right. Do the ratio test for this one. Huh? Yeah, another window's open. Okay. Okay. I'm sorry. Yeah, unfortunately, like they literally put in fake windows. All right. Just pick up the video afterwards, and if you need help, just let me know.
The factorial, it reduces, right? It's n plus one.
Yes.
The factorial would still be included on the n plus one factorial, or would it just be n plus one times n factorial?
It'd be n plus 1 times n factorial. Because you're pulling that up first term out.
Yeah.
All right. So we get this. Nice thing is this one didn't have a fraction built into the problem, so it worked out. It simplifies a little bit easier. Remember that the n plus 1 factorial changes to n plus 1 times n factorial. So the n factorials will cancel out. The x to the n plus 1 changes to x to the n times x. So the x to the n's will cancel out. Because that's x to the 1.
How did you get the absolute value? How did you get the n plus 1 out of the absolute value?
What are the values of n that I would use in a series? It starts off at 0, right? For the original series, was n equals 0. Can that ever be negative? No. So I don't need the absolute value. That's how I pulled it out. So, because absolute value just basically tells me it basically eliminates the sign. In all honesty, it tells me distance, but it's basically eliminating the sign. Since n plus 1 will always be positive, I don't have to worry about eliminating the negative sign on the other side because it doesn't exist. It doesn't make a difference. You
Is
could
it
have.
wrong if it's still in there?
No, it doesn't make a difference. Because the next step I'm doing is n goes to infinity anyway. And what is n plus 1 as n goes to infinity? Infinity. This is literally going to infinity. So this one goes to infinity for everything. Okay? So this series is never convergent.
So we know it's not convergent?
Correct.
We know that it's divergent.
Yes.
I got to this last class.
Yes. So remember this is where we did the ratio test, right? So the ratio test says it's when it's less than 1.
Oh, if it equals infinity, then it's that.
Correct. It gives me that option. That's why we use the ratio test for these, because it has both options in it where a lot of the tests don't. Okay. And this one, it goes to infinity. So I know this one always diverges. There's actually is one case where this would converge. because the only one that would converge is if x was 0. Because if x was 0, it's 0. And 0 plus 0 is always going to be 0. So technically, you'd say this one diverges when x does not equal 0. That's the official answer for it. But if you just said it always diverges, I would be totally okay with that because the 0 is a very special case.
This series is never convergent also, okay?
Yeah, that's fine. That's basically the same thing as saying divergent. I think saying it's divergent is easier, but that doesn't make much difference. Either one of those would be fine. Now, this one, we don't have to test the n cases because we don't have n cases. So, okay. All right. Let's look at this one.
You want us to use the ratios to the state?
Yeah. You can keep working on it. You have no problem right now. I will switch over and I will put the problem back up there.
Microsoft Paint.
No, I'm just using, I went back to Jamboard. I have Jamboard still works, which is good for at least for the rest of the semester. Yeah, all services are not online. Thank you. Flesh.
Allergies are kicking my ass.
All right. Same concept we've been doing. Split things up, that and put things that are similar together. So we have x to the n plus 1 over x to the n, which ends up being just x. We have 2n factorial over 2n plus 2 factorial, because you distribute the 2 times the n 2 times the 1. I have to pull out two of them to get down to the 2n factorial. So I have 2n plus 2, 2n plus 1, and then 2n factorial. So the 2n factorials will cancel out, and I have 1 over 2n plus 2 times 2n plus 1.
Why is it 2n plus 2 factorial on the bottom?
Because it was 2 times n plus 1. You're replacing the n with n plus 1.
I see.
Yeah, I wasn't sure how to deal with the 2n plus 1 factorial, because
So whenever you're replacing just the n. So that's why if you looked at how I wrote it here, that n became in parentheses n plus 1. Everything else stayed the exact same. Now I have to distribute that 2 to the n and the 1, and that's how I got the 2n plus 2 factorial.
yeah, no, I get that. I didn't know how to.
Oh, split it up?
It's like I was looking at that as a possible average.
Yep.
Like, do I distribute the 2? And then I was trying to think like, how would that get me to 2n factorial? I couldn't think.
Gotcha. Yeah, always distribute it to get rid of that, and then basically you're working down the
Because
ones.
I was seeing if I could maybe like take out like a 2n factorial without distributing.
No.
But then like the rules of parentheses prevent me to do it.
Yeah, and factorials like just like a square root type of those type of things. It's a function. So you can't like distribute the pieces, the factorial through. Unfortunately. So we end up getting x over 2n plus 2 times 2n plus 1. As n goes to infinity, the bottom gets infinitely large, so that goes to 0. So this limit equals 0.
Would there be a situation in which we also have x going to somewhere?
No.
It would only be x or n.
Well, in this case, we're looking for the values of x that will work. So you're not going to have x going anywhere. In your limits, you're only ever going to have one thing going.
I don't know how I don't know how x turned into 1.
X to the n plus 1, that part, or just the x?
I have the limit of n going to infinity of x divided by 2n plus 2
Right.
times 2n plus 1.
Right. So the x's can be any value you want. The x isn't changing, so it's not 1. It's still x. It's not 1.
You wrote 1 up.
I think I just wrote 0. Hold on. As soon as it comes back up.
We did right.
Did I?
Well, for the spot.
I thought I have it equals. I had x.
He's talking about this. One.
Oh, because there was no x at that point. That's why. Hold on. I know.
Were you talking about this part out here?
I don't know. Like, that was different.
I will.
Okay. Since that's not coming back up, let me see what you got. And then we'll go.
That's right.
Oh,
That's right, right?
that's right. I didn't have that. Yeah, I didn't have equals 1. I had equals 0.
No. You had like 1 divided by 2 and
Yes, because I was just looking at the. Oh,
2n plus
because I separated the problem. I did it like this.
Yeah.
I did this as one thing, and I did the x's as a separate piece to put together. I didn't want to mix in the x into this because I didn't want to confuse you on how the factorials were working. So I literally just looked at the factorial separately. And as soon as this comes back up, I swear to God, I'll show you that.
If it's still there.
It's there. It's just they're being annoying.
Yeah. that's
It's a
all.
nice day. Technology is not working in its math class.
Okay, it's fine.
I think this was a major-
Yeah.
So what I had was 2n factorial over 2n plus 2 factorial equals the 1 over that piece. And then I had x to the n plus 1 over x to the n equals x. I did them as two separate parts, and then I put it back together as the limit goes to x over 2n plus 2, 2n plus 1.
Alright,
Because what I was trying not to do is I didn't want, because I wanted to focus on making sure people understood how that happened without having the x in there. And then I just put them back together because you can do it. They're two separate pieces that are working. They don't interact with each other at all.
the factorials.
Yep.
It's by descending integer,
Yes.
so that's why it's a +2, that's why it's a
Plus
+1,
one, yes.
that's why it's +0.
Yes. And then the next one would be 2n minus 1,
Yeah.
2n minus 2, 2n minus 3, and so on and so forth. Now, this one goes to 0. Notice there's no more x. Because as the bottom gets infinitely large, it doesn't matter what x is, because x can't be infinity. It doesn't matter what the bottom is. It's going to be 0. So since this always goes to 0, 0 is always less than 1. So this converges for x's all real numbers. Every possible number of x, this one would converge. Yes, that's how you write all real numbers.
Is this one of those situations where we're only looking at n behavior?
Well, yeah, because that's the limit as n goes to infinity.
Because if x is like 20 and n is 1, then
Right, but we're looking at it as n goes to infinity.
okay, so it's n behavior stuff.
Yes, yeah.
So the bottom, as n goes to infinity, it will always be bigger than
Whatever x is. Yes, because x is going to be a single number.
So that whole thing is always going to 0.
Correct.
Regardless of what x is.
Correct. So therefore, this one converges for everything. All right, so we have a few situations. So for a power series, we can have it that the series only converges for when x equals a. And we saw one case that it converges only when x is 0. So it'll only converge for that one particular case. It could converge for all x's, which we just saw. That's when basically all real numbers. Or it can converge for when the absolute value of x minus a is less than r and diverge if it's greater than r. So those are really the only 3 possibilities that we have, which is kind of basically every possibility that you could possibly have. So this is one of those wonderful theorems that just like, okay, every possible option can happen.
When it says for all x, does that mean like x is
All real numbers, yeah. So when we're looking at these problems, we have 2 terms that they're going to ask you. The first one is what your radius of convergence is. And the next one is what your interval of convergence is. Yes, interval. Okay. Your radius of convergence is exactly as it sounds. It's one direction, how far it is. It's just like radius from a circle. It's from the center out. So if we look at the first case that we had, we'll look at this. So these are the 4 problems that we've seen. The very first one was the geometric series. That was x to the n. And I said its interval was -1 to 1. That's what a geometric series is. Its radius of convergence would be 1.
Radius.
I would
The-
just set up a hotspot on your phone.
It's not the internet. It's
Oh.
their service. Because if it was the internet, my Jamboard and my meet would go down. So I know that much. It's just, yeah, it's their service is not as good as it was supposed to be. So I will keep searching for a service that works. Although this is only the first time it's happened, so I'll give them the benefit of the doubt today. All right. Yes.
Are the examples that we've gone through, are they like, are all problems gonna be just derivations of those?
No,
examples?
not necessarily. These are just 3 simple case, or well, in essence, 4 simple cases to show you the different possible options that could come up. But pretty much every possibility that you're going to look at, you're going to go back to either the ratio test or the root test to do it, to simplify it down. Once you simplify it down, then you have your convergence, and we look at that algebraically to solve for what the x's are.
Is there a reason why we're only trying out the ratio?
Because so those 2 tests, I just haven't put a problem up that does the root test. The only reason we're using those is because it gives me both cases. So the geometric series, my interval of convergence was -1 to 1. The radius convergence is 1. From 0, because 0 is the center, 0 to 1 is 1. Same thing with the first example. Remember, we had the interval of convergence was from 2 to 4. Notice they wrote it in set notation with the bracket for the 2. So the radius, again, this one is still 1 because the center would be 3 to 4 is 1. So in essence, your radius, if you find the interval, the radius is just half of whatever your range is, or half your diameter, if you want to think about it in terms of circles. The second one we did, remember I said it only converged at 0. That was a special case. It diverged everywhere else. So my radius of convergence is actually 0 because there is no radius. It's literally just one number. And-
Most of them is part of what Pirate is writing down the signal infinity.
Don't write those down. Just you already have this all written down. These are the last 4 problems I did.
I know, but I saw everybody else writing them down. I'm like, I guess I'm gonna
Like you don't have to rewrite these. You already wrote these down. It was just a nice table for me to go back instead of having to flip back pages. The last one we did, all real numbers, -infinity to infinity. So my radius was infinity. Yes.
So radius of convergence is,
Radius of convergence is how wide the interval is going to be. Well, half of the distance of how wide it's going to be.
oh, well, okay.
Notice in none of the problems that we've done so far, we actually found the radius of convergence first. We found the interval first because they were basically all simple ones to come up with. The next one when due, you'll see how the radius comes into play.
For example, 2, that notation for 0, does that mean it can't be 0?
That means it's only 0.
Oh,
Remember, it diverges for everything except for when x equals 0, so it technically converges at x equals 0. That's the only value that one converges at.
so example 3 is all numbers except 0. What was example 3?
Example 3 was the one we just did. That was all real numbers.
No, example 2 was
A plug.
divergent when x doesn't equal 0.
Yes. That's correct. That's example 2. So it's divergent when x doesn't equal 0. It converges when x equals 0. That's okay. And example 3 was all real numbers. That's the one we just finished. Okay, they were stupid, updated something, and crashed their server.
Oof.
This is why I liked when Google had things that like, because Google just works. It just doesn't go down. It just works.
Well, if Google went down.
We'd be in trouble. All right, so let's look at this one. So most of the problems that we've looked at so far were pretty straightforward. Like the math and stuff of them was very simple. There wasn't a lot of numbers in them. And now we're going to get into some more, a little more complicated ones that have more stuff in them because I want to show you where the radius of convergence comes into play. And it's not always going to be just 1 or 0 or infinity. So let's look at this one. So we have same concept.
It's alternating.
It is alternating, but does alternating matter when I'm looking at the root test or the ratio test? No, because it's going to give me it's going to tell me it's absolutely convergent, so I don't really care if it's alternating or not. In these cases, technically, x could be negative. If x was negative, this is no longer alternating. So that's where you can't look at those other tests because we don't know what x is. By looking at the ratio test, we can take into account that x and then solve for it at the end. We use those other tests when we're looking at the end of the intervals to see if those converge or not because my x no longer exists. So we have the limit as n goes to infinity of -3 to the n plus 1 over x to the n plus 1 over the square root of n plus 1 plus 1.
So n plus 2.
Yeah, I'm going to combine it in a second. And then I flip this over, so n plus 1 over -3n x to the n. So my -3 n plus 1 over -3 to the n is just -3. My x to the n plus 1 over x to the n is just x. My square root of n plus 1 over the square root of n plus 2 is the square root of n plus 1 over n plus 2.
That one's easy. And we can combine it with square roots, right?
Yeah, that's what I did. So I have -3 x times the square root of n plus 1 over n plus 2. So if we divide it, the limit of that square root's going to what? If you divide them all by n, I get 1 plus 1 over n over 1 plus 2 over n. So that's going to go to 1. So this ends up being, the absolute value of -3 is 3. So 3 absolute value of x is less than 1.
I think I have trouble, like I can get to the point where I get rid of the n plus 1s. I get rid of the x to the n.
Okay.
I just don't know like what to do once I get to -3x times square root of n plus 1 over 2.
Well, the limit is as n goes to infinity, right? So the only things we're actually worrying about at this case, because of the limit, is the x. The x's I can't do anything with. Any of the numbers outside I can't do anything with at that point. I'm basically only concerned with the n's. Okay? So I would divide them all by, in this case, all by n. And that ends up being the square root of 1, which is just 1. So I end up getting the limit as n goes to infinity is of that equals just 3x, or the absolute value of negative 3x.
Is there a reason why you write it as 3 absolute value?
Yeah, because when we're solving it, I can pull out constants and things like that. I can do the absolute value, because when you're multiplication, you can do the absolute value of each piece. It's fine. So the absolute value of negative 3 is 3. So I can pull that out and not have to worry about that. The reason I did that was so we can actually look at my ratio or my radius. So do you get why you get that part, Eugene?
Yeah, I don't think I got to the same simplification as you did. I got negative 3x times square root of 1 plus 1 over n divided by 1 plus 2 over n.
Right. That's fine.
Yeah.
Now, as n goes to infinity, that 1 over n goes to 0. The 2 over n goes to 0. So now you have 1 over 1, which is 1. Okay, so we have this. Which ends up being the absolute value of x is 1 over 3. That's the radius of convergence. The piece that the absolute value of x is less than before you solve for the absolute value of x, that's your radius. So if we look, I think I had the first problem up or switched, yeah. So if we look at the very first problem we did, that's my radius, is the 1. Okay, because I've now got it down to the absolute value is less than something. Okay. Now to find my interval, I have to then solve for the absolute value of x. So I end up getting negative 1/3 is less than x is less than 1/3.
Is it negative 1/3 just because, if x is negative 1/3?
Yeah, it ends up being, remember, it's negative x is greater than 1/3, and then that gets you the x is greater than negative 1/3. Or sorry, less than. So remember, the absolute value switches into these two things. Those two things. And this, because you want to get rid of the negative sign, gives you that, which gives you that. Now, that's not my interval of convergence yet. What's the last piece that I have to do?
Plug it in.
I have to plug it in and I have to test the endpoints. Because the ratio test, again, 1 doesn't work I have to do something else with it. So we're testing x equals negative 1/3. So -3 to the n, negative 1/3 to the n is the same thing as saying
looking for
yes. Yep, we're plugging in for the x, not the n's. So this one right here is 1 over square root of n plus 1. If we look at that series right there as n equals 1, that's just the square root of n, correct? That and that are the same thing. Because this one, if I started at 0, is the same thing if I'm starting at 1. This is now a what? That's a p series.
This is technically into the 1/2, right?
And n, oh, sorry, the p equals 1/2, which is less than 1. So divergence.
why isn't p negative 1n? Because the n squared is under
Because the p series is always 1 over n to the p.
Why is
Because if it was on top, it's always divergent. Why is what?
n equals 1, and this could just be a break part? Why is it not n or 2 root 2? Oh, never mind.
Okay. That's good because I wasn't quite sure where you were going.
I didn't know either. After I said that, I was like, what's coming out?
If we plug in 1/3, everything in essence stays the same except for that's now a negative 1. Zero, not 1.
I mean, it's 10.
0 plus 1. So now this is a what? That's an alternating series. Alternating series says two things has to be true, right? It has to be decreasing. Does this series decrease?
Maybe.
So remember, we're looking at the AN, right? Or the BN, they used it. They moved to BN. So BN is 1 over the square root of n plus 1. Is that less than BN plus 1, which is 1 over the square root of n plus 2?
No.
Sorry, I have it backwards. That's greater than that. It's decreasing, correct? That's going to be bigger than that.
Why isn't the but it's raised to the nth power, does that
So you're right. So when we're looking at the alternating series test,
go faster than
well, no, that's just going to keep flipping back and forth. The negative 1 to the nth power is literally just going to keep flipping back and forth. That's what makes it alternating. Since we know this is an alternating series, I can use the alternating series test rules, which there was 2 rules for it. One, it has to be decreasing. So as long as the next term is less than the previous term, it's decreasing. And this one's not, doesn't have anything crazy that's going to happen that we have to figure out the derivative and stuff like that to prove it the top staying the same as 1, the bottom's going to keep getting smaller. That's true. The other piece is it has to go to 0, correct? As n is getting infinitely large, does this go to 0? Yes, because it ends up being 1 over an infinitely large number, which is 0. So this one, that converges based on the alternating series test, and that diverges based on the p-series.
Can we go back to x equals negative 1/3?
Yeah.
Uh,
Oh.
It's the same thing.
Oh, that picture, yes.
So once I get to 1 over square root of n plus 1.
Yep.
How did you get to 1 over square root of n?
I just changed the n to start at 1 instead of 0. If you plug in 0, what are you going to get? The square root of 1, right?
Yeah.
Plug in 1, you're going to get square root of 2. 3, and so forth, right? So if instead I start here, I plug in 1,
Yeah.
I'm going to get the square root of 1. I'm going to get the square root of 2.
Well, 1 plus 1 is 2.
Right. Okay. So this series, please tell me I'm right. Okay, because it's not showing up on my screen for some reason. This is 1 over the square root of 1 plus 1 over the square root of 2 plus 1 over the square root of 3, right? And it keeps going, correct?
Is the 1 part of the square root?
Yes.
Yes.
Okay. Is that also true?
Yeah, but like, why did we swap back to square root of n? I thought we were talking about square root of n plus 1.
We were.
Yeah.
Do we have a rule that works with the square root of n plus 1? No, we don't. Okay, because there's an extra piece there, right? So remember, there's a few rules that we have that are really nice to work with. The geometric series, the p-series, and we can do some things with comparison tests and stuff like that to show this. So in this case, I saw, okay, I have the square root of n plus 1 down here.
Yeah.
I know the p-series works with the square root of n, just the square root of n. So is there any way that I can change this to this? So now I can use the p-series.
When you say use the p-series, are you talking about the ratio test? Or
No, that's just the p-series test. The p-series test says if the power is greater than 1, it converges. If it's less than 1,
Oh,
that one. That was what we covered in section 11.3. It was 1 over n to the p. If p is greater than 1, it converges. If p is less than or
so,
equal
like,
to 1,
I
it
wouldn't
diverges.
just like I wouldn't just do the limit of 1 over n plus 1, and that wouldn't give me anything.
Well, if you did the limit of that, it's going to go to 0.
Why is that bad?
Do we have a test that says if the limit goes to 0, it converges or diverges?
Yeah.
We don't. We have a test that says if it doesn't go to 0, it diverges. But it doesn't say if it goes to 0, it converges. That's the test for divergence. So if I just did the limit, it'd have been fine, but it would have gone to 0.
So the series n equals 0 infinity of
Yes,
1 over
this.
n square root of n plus 1 is the same as
Yes.
the series n equals 1.
So infinity of
to
1 over
infinity
square root of n.
1 over.
Yes, these two
That's
series
what I
are
don't
exactly
understand.
the same
That's why I don't understand. Why are those equal?
because the actual solutions are equal. When you plug in the values for n, you're going to get the exact same thing. It's like 1 over 2, it's like 1/2 and 2/4. 1/2 and 2/4 are exactly the same thing. Correct? Yeah, 1/2 and 2/4 divide, they're both a half.
It's just that 1/n+1 and 1/n is not the same. Like,
Right.
Yeah.
This is not the same.
What am I not getting here?
I don't know. This is not the same.
Does everyone else just get this? Like,
So,
am I the only one who's not getting
okay.
it?
This is what I was trying to ask you. So.
Okay. These pieces right here, you're correct, are not the same.
Yeah.
Okay? That is absolutely correct. The series are the same because they give me the exact same answer out. Even going all the way to infinity, these two are going to give me the exact same answer out. You do not have to start at 0. I can start anywhere I want.
But if I started somewhere else, then
Then it wouldn't be the
not
same.
the same.
Correct. And that's fine. I wouldn't have set those equal. Like I couldn't say start this at 2 and say it's equal to this.
It's
Because it
only,
wouldn't
it's only when n equals 1
That
that's-
these two are exactly the same. Correct. If this said n+2,
Yeah.
I would have started at 2. And they would have been the
It's just
exact
that
same.
That's like how is I like if I encountered that, how would
You-
I arrive at that conclusion?
It's
That's not a test. That's
You're
not-
right, it is not.
That's
not. And it's actually the conversation I was having with Roxanne earlier.
like you just
Is
went over it like it was nothing and just
So-
expected me to.
no, it's fine. So series
Yeah.
in general is not the same as all the rest of the math that we've done. So in integration, all those other things, you have a very specific set of rules. You follow them to a T. This is basically like a recipe. You follow it and you get the answer. In series, there isn't necessarily a perfect recipe for it. It's a lot of logical conclusions. Okay, it's like a lot of deduction. It's like, okay, this is the same as this. That's what we looked at last class with like the direct comparison tests. We're saying this and this, they're not equal, but I know this is always going to be less than this because of the way the algebra works and the numbers work. And because I know it's always less, I can determine if it's convergent or divergent, whatever it happens to be. So these two series, this piece here, you are absolutely correct. Those are not equal. They will not give me the exact same answer. However, because they are a series and I'm looking at it as n changes, they're a distinct value of points, not a continuous stretch of points.
So-
Now it works.
so like that's a tool that we should have in our arsenal.
That's a tool. Yeah, that's a tool that you should
That like changing the starting point
could help you.
change the series to make it work for us.
Yeah, because again, series isn't continuous. Series are discrete values. You're plugging in n equals 1. You're plugging in n equals 2. You're plugging in n equals 3. You're not plugging in all the numbers between 1 and 2. And that's what makes the big difference. Because if I was plugging in all the numbers between 0 and 1, this wouldn't work. But since I'm only plugging in 0, 1, 2, 3, these work. So sometimes you might have to do exactly what I just did here. By going, and actually this is literally what the book did. They wrote out the first 3 points or the first 4 points. Okay, well, if that's the case, if I just start, that's 1, that's 2, that's 3, like that's the same. So they used that to make the conclusion, the logical jump to that. And the reason you're looking at that is we've got something that we have. It's not a P series. It's not one of those tests that I have as stated. So how can we use the information that I know to solve this one? You could have just done an integral. Remember, the integral test always works. You would have had to do the integral of 1 over the square root of n plus 1, which actually wouldn't be that difficult to do because the U substitution would have worked fine with that one. So you could have done the U substitution or the integral test for that and been fine. But remember, the P series is one of those ones that makes life a little bit easier to do. Okay. So in this case, my P was 1/2, which diverges. So that gives me that one diverges. When I plug in the 1/3, I have an alternating series now because I have -1 to the nth power. So now I'm not using the P series test, I'm using the alternating series test. Because anytime I have an alternating series, use that test, life works out nice. The alternating series test is a very nice test because it only asks 2 things. Is it decreasing? And does it go to 0?
Yeah, no, I understand the X.
So
The X equals 1/3.
that one makes my life easy.
Then I.
So we have this. I know the first one diverges and that one converges. So my interval of convergence, that's my interval of convergence. Is parentheses negative 1/3, comma 1/3 bracket. Square bracket. Okay. I want to find one because everyone we've done is the ratio test. I want to find one that does the root test. So give me a second.
They don't exist.
They do. They're just the ratio test is like the main go-to in this one, but the root test works. So it's like I want to find one that does the root test. $25. Okay. All right, so let's look at this one. So in this one, the question is why? I already said we're using the root test. So the question is how, what when you're looking at this problem, because I think that's the next piece that we need to start looking at. It's like, why am I going to use this test for this? Why would I use the root test and not the ratio test? I'll let you answer in 1 second. Yes.
Is it because you could get the whole thing raised to an nth power?
Yes. That's the reason. If I could take the entire problem and raise it to the nth power, root test, because that gets rid of the nth power. So I can take this and change it to, I'm not going to rewrite this thing there, but x minus 2 over n to the nth power. Those are the exact same thing. So now I can do my root test. So n over, oh, sorry, the limit. And again, that has to be less than 1. Because the root test is the same as the ratio test in terms of convergence and divergence. So as n goes to infinity, what does that go to? Because remember, x is not changing, x is a single number. So this is always going to 0. And 0 is always less than 1. So my radius of convergence is infinity. My interval of convergence is negative infinity to infinity.
Sorry, I thought
Yes.
the radius was 1/2 of like your interval. So,
Yeah, what's half of infinity?
but like it's from 0 to 1, so
No,
that's the interval.
no, my interval is in negative infinity to infinity in this case. So notice there's no more x. Okay. So if you remember in
It's like the previous ones.
correct. In this problem,
Yeah.
I have an x left. In this one, no x. So I have nothing to solve. Because the x can be anything. Doesn't matter what the x is, it's always going to be 0. Okay. And this is actually, so remember I said x can be anything? Except what? What can x not be? Right. Doesn't include infinity. Because then I would have infinity over infinity, which is inclusive and I have to go to stuff. That's why the parentheses have brackets. And that's also why we don't have to test the endpoints because they don't work. Okay. And infinity divided by 2 is still infinity. So that's why I don't have my radius as half of infinity because it's still infinity. So there's a root test or a root test. How could I do this? Let's do. I'm just trying to find a good one to end with. Let's do this. All right.
The first step for this problem to put together 5x minus 4 and somehow like put that together.
No, first step is do the ratio test. Yeah, just do the ratio test on it.
I thought we're
No, you can't simplify this one down and break
I
it
was
up.
trying to make it work for the root test, but
Yeah, no, don't do this because if they were both to the nth power, root test.
yeah, no, that's pretty fun.
Yeah, they both have to be the nth power for the root test. Actually, most problems you're typically going to have that raised to the nth power, but something else in it's going to prevent you from doing the root test.
We want to distribute n+1 cubed, but do we want to like multiply that out?
No.
That does go like that.
I'm just finishing up the problem so everybody can see it once I'm done.
That's good to do. You just put it back into the original, or?
Yeah.
Good, so put those together and find the one that's that, because this you can ignore with the one that's you want.
Uh,
Ignore this. Because that doesn't have anything. Let's be a little more like that. Put your radius.
And once I get here,
That's fine. I'm looking at it where you are.
No, because it's just the,
no, back here.
it's just, it's the series or whatever, right?
I'm pretty sure it is a series, but.
Remember that keep those.
So what do we do with these?
The Jackson's all
Wait,
one
so
fraction,
isn't it
the
this
deal
one
with that,
is-
and all together in one
Wait,
fraction.
one of them is and one of them isn't. Because the alternating is,
So, you know, my brain is fucking cooked.
isn't the bottom?
Keep
one-
going.
Wait.
There's a reason I
it's
fixed
two,
this
but it's
problem.
not. Wait,
Mr. Baker,
I'm there, one second. Try something. I'll bet it's very good. And it's not n-1, it's just like 8n plus 1 over 8. Or 8 something.
that is,
I don't find it.
this one's,
I don't know what to do with that. I know this is serious, but
Okay, this is all correct.
awesome.
Okay, so you're plugging those values in?
Yeah.
Okay, so you got that?
I just, yeah, I just don't know what this, well, I could go back and look at it.
Well, what's that?
that's an alternating
Right, and that's gonna be,
divergent, because that's just the,
nope, it's 1 over n to the third.
oh,
It's not harmonic.
Yeah.
So this one's alternating, so use alternating series test.
Yeah.
This one's just 1 over n to the third. That's p series.
oh, P series works.
I don't know.
That's good.
But like, shouldn't I do out as I want? Like, shouldn't I do?
No, because this is all, okay,
It's
sorry,
divergent because it's greater
one
than
extra
one.
step. Remember what I did at the ends to get to the root test? You put them together, correct? Actually,
I'm alternating series
a lot.
test.
I don't know what's about
Now they will take this and make it this.
that. It's just
Because
big.
they're both for the entire. They're both for the third column. Look at this.
What's alternating series test is,
Two steps. Does it decrease? Does it go to 0?
thank you.
And in all, don't tell any other math teacher in the world I said this. You only actually have to care about the bottom part. Because if it doesn't go to 0, it's not decreasing. So I always test that one first. Does it go to 0? If it goes to 0,
Sure,
gonna pass the alternating series test because it has to decrease.
I guess the case is 0.
Well, what's the top?
-1.
No. Remember, the alternating series test ignores the sign.
Oh,
So it's 1 over
1 over.
n to the third, which we know goes to 0 because as n gets increasingly large, it goes to 0. So it goes to 0, so therefore it passes by the alternating series test.
Which makes it n converges.
Correct. All right. So that's step 1. You should have gotten it down to the absolute value of 5x minus 4 is less than 1. Now, at this point, you might say, oh, my radius is 1. There's always the reason I give you problems. Okay? Because I said, oh, it's just whatever that is. Problem is x not really by itself? There's something in front of the x. So in some situations, and this is one of those cases, I always find my interval of convergence first, and then I will look and find my radius. Even though it asks you typically the radius first, and then asks you for the interval of convergence, I always find my interval of convergence first because it makes my radius really easy because I just look for half of whatever's there. So I always do it backwards. So we've got the 5x minus 4 is less than 0, is less than 1. We solved this. I now have 3/5 is less than x is less than 1. Because I added 4 to both sides. And then divide all sides by 5. So from 3/5 to 1, that's 2/5. My radius is half that, so my radius is 1/5. Now we plug in 3/5 and 1. If you plug 3/5 into this, the top becomes just, it's 3 minus 4, which is -1. So it's -1 to the nth power over n to the third. That is an alternating series. It is decreasing because you should remember, once you look at the alternating series, you've determined it's alternating series, you're looking at just the b to the n, which is not having the negative sign in it. You're just looking at the series as it is there. So I have 1 over n to the third, which is decreasing. And it goes to 0 as it goes to n, the limit goes to 0. So therefore, that is convergent by the alternating series test. If I plug in 1, I get 5 minus 4, which is 1. So I have 1 over n to the third. That is not alternating, but that is a p series with p is 3. 3 is greater than 1, so therefore that is also convergent. So this one is square bracket 3/5, comma 1 square bracket. They converge at both of the endpoints. So not every situation does it only converge at one endpoint. So because what's 3/5 minus 1 is 2/5. Half of that is 1/5. The diameter is 2/5. The radius is 1/5. It's, in all honesty, it's literally just like a circle. It's from the center out, and the center in this case is 4/5. So, okay. All right. One more thing to go over on Thursday. Actually, no, I took the test this week, so I have a few more things. I have a little more time. Okay. I still have to do. I have to get to Taylor series, which will be next week. I will see you guys on Thursday. Okay. Oh, and before everybody leaves, I can't smell to save my life, so I literally have no clue whose perfume set her off. But if we can lessen it, it would be helpful. So, like I said, I honestly I can't smell to save my life, so I literally couldn't tell you who or what.
Must
So,
definitely be. I work in a Sephora and I have perfume break on me today.
oh,
That's
then-
my fault.
okay, sorry. That does suck though.
Yeah.
Yes.
Just checking, I did tell you about
next Thursday.
Yes, you said you weren't going to be here.
Yeah,
That's fine.
and we're just going over like no tests or anything, just over stuff.
Next Thursday?
This Thursday.
This Thursday, I'm doing power series representations
Okay,
of functions. So
So-
at 11:09.
so I'll be fine.
Yeah, you'll be fine.
feel like because nobody asked questions, everyone just gets it.
No,
And that makes me fucking mad. That
Eugene.
everyone seems to be getting it.
no, no, no. Honestly, most people don't ask questions because they're completely and utterly embarrassed about asking questions, and they just don't feel like asking them. Which is why, as some teachers